Okay, calculus is often considered the mathematics of change, and this lesson here is all about that. It's about the idea of a rate of change, so connected to the idea of differentiation or the derivative in calculus. So the basic thing we might recall from algebra is this simple formula, right? Distance equals rate times time, and then you can rearrange this. Right, where rate is equal to distance divided by time. So the key here is when we talk about this rate, this is an average rate of change. So this is not considering a rate or a velocity at a moment in time, but it's an average over a certain interval. So I want to build this idea just a little bit. So we're going to look at some basic ideas here. So typically in physics, we would write down S of t as standing for the position of an object. So this could stand for where something is. So S is position and t is time. So we can mark a moment in time here, like t, and we can say an object is at a certain position. And then a few moments later, so this is a new moment here, t plus h, we have a new position. Right, so S of t plus h. So the basic idea when we talk about an average rate of change is we use this formula, the distance divided by the time. So if S stands for position, then we're going to subtract these two, the finishing position, and then take away the original. So we're going to write this down here. And then we divide by the time that has elapsed. So you can see from t to t plus h, h is the elapsed time. So this idea will look familiar to you, and it's a very important one. And so this basic idea is the average rate of change, right? So it gives us the average rate of change of this function over the window, right, from t to t plus h. So the interpretation here, because we're talking about rate, is an average velocity. So this is the general way that we think about this. So this expression here gives us the average velocity, right, of this particle on this window from t to t plus h. Okay, so this is going to change a little bit when we shrink the window. So if you look at the original window here, ranging from t to t plus h, what we're now going to do is to take these 2 points and to let them get closer. So we're going to let the second point get closer to this one, and the idea is that h is shrinking. So in this expression here, we're going to let h approach 0. So this is going to give us something new. So what we can do is to repeat this idea, but we can just write the limit as h approaches 0 of the average rate of change. So I'm repeating that. So then we have a new basic idea. So I'm going to focus on this principle now. So this is a different idea. It still corresponds to rate, right, because we have the same expression here. So in mathematics, this thing here that we're seeing in red is known as the instantaneous rate of change. So because our interval has now shrunk to a single location, this is giving us the rate of change at a single spot, right, a single moment in time, because h is approaching 0. So the way we describe this mathematically, again the result in red, this is the instantaneous velocity at precisely this moment, t. So again, when we look back at the number line, okay, originally we were talking about this window here, and now because we're letting h go to 0, now we're really focusing on the single point. So this is a instant in time, hence the name instantaneous rate of change. So the big thing to learn here is that this here is giving us the velocity at a single location. So in physics, it is this thing here that is known as v of t. Okay, and we recognize this here as being the derivative of the s function. So when we differentiate the position function with respect to time, we get this new function, which is the velocity function. So we should take a minute right now just to formalize all of that. Okay, so taking all of those ideas together, so S of t represents the position here if we're talking about something like linear motion. And then this idea gives us the first important fundamental principle, right? And that the velocity function is the derivative of the position, right? If we have the relationships that we previously saw. And you can derive in a very similar way the acceleration can be obtained also by differentiating this function here. So the acceleration is the derivative of the velocity, but then you could also interpret that as differentiating the position function not once, but twice. Okay? And these are pretty well-known principles in physics. So these important functions of position, velocity, and acceleration are all connected via rates of change. Okay, so I just want to throw a couple of ideas up here that are important. So this is almost a review of what we just talked about, but this is just to make it a little more formal. Okay, so when we have any kind of function, if you look at this setup, right, the difference quotient, this is going to give us the average growth rate of s, right, on this window from t to t plus h. So notice here, all we're doing here is we're dividing by the distance that has been traveled here over the elapsed time. So if s means something different, if it can be interpreted as something different than position, then we're still going to have an average growth rate, but it will indicate the average growth rate of s. So the key here is we have an average here, and all we're doing is a simple algebra, just dividing two ideas. Okay, so this idea changes completely when you want to look at the instantaneous growth rate. So if you want to look at the instantaneous growth rate with respect to time, this is corresponding to a single moment in time, and so as we saw this in the derivation, this is no longer just an algebraic idea, so this involves the derivative ds dt. So you can see instantaneous corresponds to finding s prime. So that's the real big connection to make here. Right, so just to give you a couple of concrete examples. So I'm just going to put these two expressions back up here, and then we can just talk about some different scenarios. Right, so these are definitely related ideas, but at the same time they're quite different. So in our first example, the function we were looking at was position. So you could be looking at something like the way that a population grows, and we can understand this as the average growth rate. And then you can think about just the plain old growth rate, right? So this is at a specific moment in time. So again, when we talk about a population, this could be the population of people or the population of foxes, even something like the culture of cells, right? Something like that, so just how the cellular population grows. Also, your function might be something like, it might tally the cost of living, it could tally temperature, for example. Right? So these ideas of an average growth rate and an instantaneous growth rate will apply to all different types of functions, right? Just depending on what that function measures. Okay, so I want to close here with an example. This one comes from physics. So we're going to look at a free fall problem. We'll watch a falling penny and then study a couple of different things about its motion and also its speed. So we're going to go with a basic equation for free fall here. So this is provided in the problem. And what I'll also try to do maybe is to draw a picture to describe some of this. So S here is representing the position of the penny, right? The position of the coin. Okay, and then based on the data that we're collecting here, t is going to indicate naturally time. This will be in seconds. And then s represents the position, right, or the height of the falling penny. And this we will record in feet. So based on this, we're just going to try to answer a couple of questions. So this will be the first one we can take a look at. Okay, so this question here. So we can probably take this one down and answer this. So the first question here says, on average, what is the velocity of the penny between the first and second seconds of flight? So what we're trying to imagine here is we're dropping the penny from the top of a building, and then somewhere between the first and the second seconds, we would like to know, on average, over that window, how fast was the coin or the penny actually moving. So we'll try to understand this. I'll draw a little picture of this just to grasp the scenario. So we have the building here. Okay, and we're going to watch this penny fall. So the penny is going to drop like this. And so this equation here is going to govern the motion, right, of the penny. Sometimes it is very helpful to graph this function, right? And you can see this will be a parabola opening downward. So if you were to graph the function, you get a little bit of insight on what's happening. So you can see that over time, right, the penny is dropping, right? Eventually it's going to hit the ground. You could also see the parabola begins at 1300. And what that really means is that corresponds to the height of the building. So the 1300 indicates 1300 feet. And an important thing to understand is this is not mapping the trajectory of the penny. This is simply telling us that as time goes by, right, on the x-axis, we can follow where the penny is. Okay, so if we think about this question, this one is all about average, so we can go back to our basic formula, right? The rate is equal to the distance traveled over the time that has gone by. So this is saying what's the average velocity in between the first and second seconds. So as the penny begins to drop, we could probably take a snapshot and say after 1 second it is here, and then maybe after 2 seconds the penny is here. And this question is all about if we could calculate how fast the penny is traveling here, we want to know on average, right, what is the speed of the penny over this window. So this does not involve any calculus. We can just calculate the distance traveled divided by the time that has gone by. So to calculate this, and this would be an average rate of change, right, so this would be the AROC, we're going to just divide a couple of numbers. So the distance traveled, because this is position, this here would be s of 2 minus s of 1, right? And then on the bottom you divide by the time that has gone by, 2 minus 1. So you can see this looks like a slope, a change in y over change in x. So to calculate this, you would just be using this function, right, your s function twice. Calculate s of 2 and s of 1, and then work out the mathematics to figure that out. Okay, so I'll let you work out the mechanics here. This is fairly simple to do. So this ends up being negative 48, right, feet per second. So this is what we get here. So the important thing is that the 48, right, is really indicating the speed of the coin on this window right here, and the negative is indicating the direction of the coin. Because remember that the coin is moving downward, and that was also something that we could see directly in the graph, right, even when we don't talk about velocity, because this is the graph of the position of the penny. Okay, so once we understand that, now we're going to move on to a different kind of question. And this is one where we can see some similarities, but it certainly is different. And this question is saying now, what is the coin's speed at precisely 2 seconds into flight? So this is a very different question than the previous one. So it is saying, really, if we could zoom in on this location right here at this spot, right at 2 seconds, the the question becomes, if we could take a snapshot of the coin there, how quickly is it moving? So this here is the idea of shrinking the interval to a single point. So this is where we need the derivative idea. Okay, so to do this, we're going to differentiate this function. Right, we're going to find s prime. So s prime of t, right, we can use the power rule. This will be negative 32t, right, and then this will become 0. So this s prime, as we previously saw, this is the velocity function. So v of t is negative 32t. So if we would like to know what is the velocity at time equals 2, it's a simple matter of letting t equal 2. So v of 2 here is going to be negative 32 times 2. So this will be negative 64, right? Same units as we see here, feet per second. So it is important here to interpret this with care. First of all, it's saying, what is the coin's speed? And when we talk about speed in mathematics or physics, we're really not talking about the direction. So we could argue here that the speed of the coin is 64 feet per second. But if you want to think about the velocity, we also talk about the direction of the coin, which we already know from the previous task. So the big thing is to look at the magnitude of these two numbers and to make sure they do make sense. So the magnitude here at time equals 2 is larger than the magnitude on this window here. And so the reason we expect a number in magnitude to be bigger is because the coin is moving faster. So we have negative 64 feet per second. The coin is moving quicker at the end of its interval than it is as an average speed from 1 second to 2 seconds. Okay, and finally we'll just ask a question that people just like to ask. It's good to know. When is the penny going to hit the ground? Okay, so if we want to think, when is the penny going to strike the ground, we're really thinking about this situation here. And we talked about earlier that this is the height of the building, the 1300. So when the coin is at rest down here, we really want this position here to be 0. So the simplest way to go about doing this is to simply set s of t equal to 0, and then solve for the time moment. So we're going to put a 0 right in there. So 0 equals negative 16t squared plus 1300. And then from this point, you can just solve for t. So I would bring this over to the left. And this should answer the question for us. So I'm going to move this to give me some room. And so you can divide by 16 and then take a square root. So we can see where this is going. And time here, we want it to be positive, right? Positive direction. So we'll take plus the square root 1300 over 16. And then naturally, you can estimate that. And you'll find this is pretty close to 9. Okay, so we can give our answer here. T is about 9 seconds. It's a pretty sensible answer here, thinking about a building that's about 1,300 feet. And of course, when we're doing this entire problem and using this equation, we're assuming there are no external forces, right, that are acting on the penny.